Hello and welcome to Yageo Group Design a Day Automotive. Today's topic is BMS Magnetics. My name is David Adib, Senior Technical Marketing Engineer here with Kemet in Florida, and I will be your host for today's presentation. Thank you for joining us here today as we discuss BMS Magnetics. Our presenter today is Mr. Robert Frost, Pan Product Manager with Pulse Electronics based in Europe. Before we start our presentation, I have some important information for you. The expected duration of today's presentation is 25 minutes, followed by a 5-minute Q&A session. In an effort to have the most optimal environment for everyone involved, attendees will be muted during the presentation. But for sure, we invite you to ask us questions. You can address your questions at any time during the presentation with the Q&A function of the Zoom session. Please, if possible, note also the slide number to which your question is related. We will answer your questions during the Q&A session. If we run out of time, you can also submit questions at go.kemet.com/DID-contact. We will follow up with your question directly after the event is over. Also, this presentation will be made available for on-demand viewing after the event is over. Lastly, once Design a Day is over, you will receive via email a short survey. Your feedback helps us to improve our future events. With this information, I hand it over to Robert. Hello, Robert. Thank you for your time today. Robert, please tell us a little bit about yourself and then begin your presentation.
Thank you, David, and good morning, everybody, and welcome to this session. I'm Robert Frost, the Pan Product Manager for Pulse Electronics Europe. I've been working with magnetic materials for over 35 years and have been at Pulse for over 20 of these. This presentation gives an insight into a small but important segment of the automotive EV market, the charging systems, and particularly the BMS magnetics required for the communication. We will look at the numbers behind BMS, the features, some product design information, a bit of third-party activity, and hopefully, as David said, we'll have time for a few of your questions at the end. So let's look at the numbers driving the BMS. The global car market outlook back in 2015 appeared to be healthy and predicted steady growth, with combustion drives, gas and diesel here, being replaced gradually by electric drives, battery, full hybrid, half hybrid, mild hybrid. And by now, 2020, 2021, 7% of the total electric powertrains would be produced. And in 10 years' time, 48% of the total powertrain worldwide production would be electric. This was being driven by regulation, technology, price, consumer choice, and changes in needs. But did it really happen? Well, the global new car sales fell by 16% in the last 2 years, and it didn't reach the predicted 100 million milestone. And in particular, Europe down here had a very bad time. But if we look at the top 10 EV deliveries by model and manufacturer for the first half of 2018 to 2019, you can clearly see that Tesla Model 3 had an exceptional year, with over 100,000 more sales than any of its competition. The previous leading car, the Nissan Leaf in 2018, fell. So there's a big demand for electric cars, and this was being driven by the Chinese. And you can see the combined manufacturers here of Geely, BYD, BEVJ, and SAIC, taking up 6 of the 10 top 10 slots. And it accounts for 45% of the market share. 33% is for Tesla. And poor old Nissan and Renault saw their share drop by 50% to 23%, 22% in the coming years. So what happened in Europe? Well, in 2017, everything looked okay. It's following the trends, around 16 million cars each year. Then in 2020, we saw a sharp fall, mainly in diesel and petrol engines, around 40%. But this was buoyed by an increase in the electric vehicle market from 9.5% to 23%, roughly around 2.8 million vehicles. And this ties in well with the launch roadmap that was given by the manufacturers from 2015. They stated that in 2019, 2020, they would be launching between 20 and 30 new models every year from 2020 onwards. And this is why it's important, because the car manufacturers are committed to the electric drives of the future. And the next 3 years are very important for designing BMS parts into e-vehicle powertrains in Europe and beyond. So what is BMS and what can Pulse offer? A quick overview of the powertrain is needed. The numerous opportunities within the EV powertrain infrastructure that Pulse has advanced products for include inductors, transformers, chokes, as well as some of the antennas for our wireless division. But for now, we're going to concentrate on the battery management system. And for that, we just need to recap a couple of things. The battery management system is made up of 3 main elements. The large battery pack, made up from smaller cells and linked in series. And this can give the required high power voltage of 300 to 400 volts. The inverter converter, this converts the stored DC electrical energy into usable AC voltage and powers the vehicle's electric motors to drive it forwards. A few of the manufacturer's choice of motors are here, ranging between 60 and 150 kilowatts. And not least, the battery management system itself. And this monitors and controls the health of the battery and the state of charge. And it's a very important piece of the drivetrain. The BMS is itself in 2 main features. The cell monitoring controller. This looks after the battery cells in real time, checking the temperature, the state of charge, as well as balancing the cells, preventing it from overheating and incorrect charging cycles, and switching out any damaged cells to prolong the life of the battery. And the battery management controller is the module that collects the data from the cells and sends it to the central ECU and drive control system within the vehicle. It relates the state of charge to the driver via the dashboard with the battery voltage, temperature, and the amount of range left. And it's important that these communication links between controllers and the ECU remain secure and safe and reliable. To do this, they use SPI, or serial peripheral interface, as it meets the goals for the short distance required. It has a fast data rate at real time, up to 4 megabits. It's reliable and secure. It's tried and tested across many industries. It has a universal multi-user base. And most of all, it's a low-cost solution and a 2-wire connectivity. By creating a master-slave setup, as shown here on the left, the master can talk to all battery controller monitors using a simple daisy chain connectivity. And if required, the last slave can be connected back to the master to create the ring topology, which supports a redundancy should any link fail in between. For the car manufacturers, it's a balance of cost, security, and safety. However, safety creates its own problem. Because with all the batteries linked together in series, there is a high potential between their output and the chassis ground, maybe 400 or 800 volts. The serial interface bus itself must be isolated and independent from the rest of the car. And here's where the transformers are used. They're chosen over capacitors for coupling the BMS circuits due to the large creepage and clearance distances that are required. These are stated in the safety standards, which the working voltage of above 70 volts DC or CELV can be as wide as 22 millimeters. The most relevant safety standards are listed here. Sorry. Our catalogue range of products include single channel transformer and choke, and dual transformer and choke for the slaves, as well as simple only transformer solutions for high isolation for the master controller, and single external choke modules. These are all manufactured in an ISO AFT production site and pass AEC-Q 200 and have complete PPAP and design documentation on request. So how does Pulse Magnetics enable BMS? For transformer design, working with third-party IC houses is key. It starts with benchmarking the electrical performance using standard designs, and working alongside the IC house, we can zone in on the parameters of the transformer to optimize its performance for signal integrity and quality. Our experienced electrical engineering team work beyond basic parameters for inductance, leakage, winding capacitance, and resistance, specifying high-frequency test and measurement limits for parameters such as return loss from 100 kilohertz up to 1, 4, or even 40 megahertz, common and differential mode rejection for noise from 1 to 100, even 200 megahertz. And we qualify the whole product from -40 to 105, 125, and probably for future requirements, 155. But the most important is compliance with the IC vendor's BMS communication signal shape. And this is a key. Here's a comparison here between a Pulse-designed one-to-one transformer and its competition. You can clearly see that our solution produces a nice, clean, sharp, square waveforms, whereas the competitors looks like a spiky sine wave, which may be misinterpreted as a transient spike and ignored by the battery management system, which could lead to catastrophic failure. Therefore, the cleanliness and signal integrity is a very important part of the design. Once the design has been fixed, we then have to choose the package to support the application and demands. And this is where the real world requirements step in. This involves understanding the safety and the working voltage. Because safety is a major concern for all car manufacturers, working battery voltages in most petrol diesel engines was around 12 to 48 volts. It's relatively safe and low, but electrical drives require 10 or even 50 times more energy storage at 300 to 800 volts, enough to drive the 60 to 150 kilowatt motors. There's also a lot of standards and regulations providing guidance for electrical safety at these voltage levels, but not all are relevant. Here are a few, and the main consideration for designing we have listed here. And these suggest they're the ones that your designers should be familiar with. Battery management systems should consist of class 1 equipment, because we have defined solutions which reduce the ability for a shock to the user. EV vehicle voltage class B, with a maximum systems voltage of 60 to 1500 volts. A maximum working voltage, according to IEC 606264-1, of 600 or 1000 volts. This helps to keep the product small, because designing above 1000 volts causes its own problem. Overvoltage category 1, pollution degree 2, impulse transience rating of 400 volts DC, as this also covers the insulation strength isolation for 1 minute, which when calculated for 1000 volt working voltage comes at 4.3 kilovolts. And it also guarantees the 15-year lifetime of the isolation being a greater than 1500 volts. Some of these requirements have no bearing on signal transformers for BMS in the standards, such as continuous voltage. But because transformers are considered an integral part of the high potential powertrain, isolation to chassis ground and a need to protect the user from hazardous shock means that we have to adhere to them, even though they seem odd. By selecting the working voltage for our catalogue parts at 1000 volts, we can cover nearly all current and future needs of EV powertrains. Above this level, we would consider it to be a custom solution. The electrical performance and design is complete and frozen. The working voltage is selected at 600 or 1000 volts. Now we must fit this design into appropriate sized surface mount header to meet the necessary safety distance for creepage and clearance. Creepage is the distance along an insulation between two conductors, and clearance is the distance point to point between two conductors. These two physical parameters define the actual size of the surface mount header, and it's a very important stage of the design. For clearance, it's just normally pin to pin, or distance here shown in red. And for creepage, it can be more complex with considerations for the coil and core. If the coil and core is considered a conductor, then creepage just A plus B. If the coil is considered to be non-conductive, then the creepage is A plus B plus C. It's a lot larger, almost equivalent to the clearance. But if a longer path length is required, then we can introduce shielding or baffles, and then the core creepage distance is considered to be D plus F plus 2 times the distance down. So underneath is considered conductive. So with all these different design, we can create different solutions with different creepage and clearance. On this table here, we can see that by choosing a category with 10 millimeter creepage and clearance, we cover a variety of different solutions with different pollution degrees. The tables link together the material group, which is the ability of the plastic to conduct the pollution degree, which is how open the design is to dust or water, the working voltage, which is the battery output itself, and the type of isolation or insulation needed, be it basic, which is 1 layer, or reinforced, which is 2. For basic, this table gives 10 millimeter creepage and clearance for 1000 volts, pollution degree 2, material group 3. This is a very generic point that we use for designing. Either side of this can be used with specific changes in material and working voltage. And this is what drives the shape of the catalog products that we have. In some cases, we have to consider mechanical constraints such as height, length, and width. As most BMS circuits sit on top or on the side of battery packs, height is often fixed to 6 or even 3.5 millimeter. And that is where we developed these new packages from. So we have a complete system, and now we're relating for reliability testing to ACQ. I won't go into ACQ testing. I'll just highlight the major design features that our finished transform modules have, which enable them to pass ACQ 200 and become a fully released production component. We use previously successfully launched automotive parts like HM1188NL as a base for new BMS parts, and use similar construction methods, materials, and techniques. The surface mount header has molded in pins and is made from DAP, a high-grade engineering plastic that gives good thermal reliability, low CTI or creepage and shrinkage. This helps the component to pass the 1000-hour heat exposure and 1000 temperature cycling from -40 to 125 every 30 minutes. It also supports good coplanarity and PCB retention under ACQ bend and flex testing. The coil or core designs, in the case of options with chokes and dual channel designs, are held into the header using a reliable bonding material called Dow Corning 12577. This performs well under thermal stress and vibrations and has a low impact on the coil's performance, which is another key design aspect of consistency when subject to prolonged temperature and thermal shock. The solder terminations of the coils are inside the header. This gives them protection from external damage when overhandling, and is 100% tin on nickel on copper lead frame. They're also dipped to achieve all-round solderability to JEDEC standard JTD 002 and have an MSL of long shelf life of 1. All completed designs are supported by PPAP Level 3, full AEC-Q 200 test report, and ISO IATF manufacturing sites. We also have our own continual reliability testing, which monitors production builds and DPPM rates. In summary, the best place to start any BMS design is with the IC vendor, as this is where you'll find 80% of the approved products to start your design off. If you're unsure of the total system requirements, our FAE team can help, but you should be able to answer a few of these design-related basics, like the temperature operating, the size, the working voltage, the need for a choke. And the next slide shows a few of the IC approved products that we have in our catalogue. It's a little bit of an eye chart, but you'll see that we pick the creepage and clearance distances. 22 millimeter is very long, 10 millimeter is more standard. We have the working voltage, 600 volt or 1000 volt. We have the high pot requirements. Again, it depends on the system itself, but 4.3 kV is a standard. And then we have the size, whether it has a choke, the operating temperature, and the chipset that it's been matched to. I've also included 2 EMC parts, an external choke and a ferrite bead, which appear on the NXP design, which we'll see a little bit later. But these 10 or 12 parts are the building blocks for any BMS system using the ICs from Linear, Maxim, Texas, NXP, and ADI. So some of the third-party approvals we have, this is the NXP solution, where HM2102 and 2103 have been used extensively and revised different formats. 2106, 2108 are long, thin versions of it, and 2112 and 2113 are new, upgraded, low-profile versions. For Linear, we have a very similar, the same solution for Linear is used for NXP. For Texas, we've had to create some new parts. The 2146 and the HM2147 are new and releasing this year. And they replace the HM2105 and 2129. For their other chipset, again, a new chipsets from Texas, the 2146 and 2147 are approved. Infineon is late to the market, but have a chipset. Again, it's a 2 cell sensor and management controller. And we have taken some of the older designs. The 2103A is a tweak, while the 2106 is used again for NXP, along with 2112 and 2113. So a lot of repeat on the same designs can be used again with different chipsets. For Maxim, they have a slightly different solution. And we have designed again some different parts, the 2136 and the 2145, which is a reinforced one for residential use rather than automotive use. So covering the whole of the battery management system, Pulse offers product on the power side for the BMS, from inductors, switch mode power supplies, DC transformers and DC converters for onboard charging, and also the Ethernet and PLC communication transformers for talking to the devices on board. And not forgetting, obviously, the wireless group with the Wi-Fi, with GPS, LTE, and Bluetooth, and also the NFC for charging at charger stations. I hope you've enjoyed the presentation, and thank you for listening. Back to David for questions.
Thank you, Robert, for your presentation. That was very informative. Let me see if we have received any questions. I'll give it a minute here to see if any questions trickle through. Okay, thank you for attending this presentation today of Design It Day. If we did not get to your question, or if you have any additional questions, please submit your question to go.chemet.com/DID-contact. Please be sure to check out the other great presentations today. Until next time, we wish you the best and goodbye.